Hello there, future doctors. Welcome. Today we're jumping straight into a super fast revision of a chapter you just can't skip in NEET physics, units and measurement. This one's a classic, so let's get right to it.
So here's the big question. Do you want to lock in a guaranteed 4 marks from this chapter? Of course you do. This topic is, relatively speaking, pretty easy, it's high scoring, and its ideas pop up all over physics. So let's make sure you nail this.
All right, first up, the absolute basics, units and the SI system. You got to think of this as the foundation of a building. If your foundation is strong, everything you build on top of it will be rock solid. Now, for this rapid review, we're really going to focus on the hot topics. You know, the ones that come up again and again, like significant figures and dimensional analysis. But hey, don't forget, a full review of errors and instruments is also super important for your exam.
Okay, let's kick things off with a simple but, honestly, a really important question. How many types of physical quantities are there, really? It's 2. You've got your fundamental quantities and your derived quantities. Here's an easy way to remember it. Think of fundamental quantities as the basic bricks of physics, like length, mass, and time. You can't break them down further. Then, the derived quantities are like the buildings you construct with those bricks, like speed, which is just length divided by time. See? Simple, right?
So, all over the world, scientists use a common language called the SI system to avoid confusion. In this universal system, how many of those fundamental or base quantities are there? Go on, take a guess.
The magic number is 7. And here they are. Length, mass, time, electric current, temperature, amount of substance, and luminous intensity. You absolutely positively have to learn these by heart along with their SI units. No way around it.
Okay, let's move on to a topic where, let's be honest, students often make some silly mistakes and lose easy marks, significant figures. Let's master these rules so you can save those precious marks.
So when you're doing calculations, multiplying, dividing, adding, subtracting, how do you decide how many significant figures your final answer should have? There's a very specific rule for this. Do you know it?
Okay, now you've got to pay close attention here, because there's a key difference. For multiplication and division, your answer is all about the number with the least significant figures. But for addition and subtraction, you look at the least number of decimal places. This little difference is so important. Please don't mix them up.
Let's try this out with a real problem. Say a substance has a mass of 5.74 grams and it takes up a volume of 1.2 cubic centimeters. We need to find its density, but we have to use the rules of significant figures.
Right, so we all know density is mass divided by volume. If you plug that into your calculator, you'll get a long number, like 4.7833 and so on. But hold on, we're dividing here, so we have to follow the rule. The mass, 5.74, has 3 significant figures, but the volume, 1.2, only has 2, and that's the decider. Our final answer must also be rounded to 2 significant figures, so 4.7833 becomes 4.8, and that's the correct answer.
So here's your quick tip for NEET. Whenever you're doing a calculation, always look for the number with the least significant figures or decimal places. That one number is the boss. It tells you how precise your final answer can be.
Now let's talk about what I like to call your secret weapon for physics, dimensional analysis. Seriously, think of it like a superpower. It helps you check if crazy-looking equations are even correct, and it can even help you solve problems.
So where exactly do we use this superpower? What are the main things you can do with dimensional analysis in physics?
Well, it has 2 main uses that are super helpful. First, you can use it to check if an equation is dimensionally consistent, which is just a fancy way of saying you check if the equation even makes sense. And second, you can use it to figure out the relationship between different physical quantities. Both of these are incredibly useful for NEET.
Okay, let's test out that first use with a classic equation you all know. Kinetic energy equals potential energy. So, is the equation half mv squared equals mgh dimensionally correct? Let's find out together.
So, let's break it down. First, look at the left-hand side, the LHS. That half is just a number, so it has no dimensions. Mass is m, and velocity squared is lt-1 squared, which gives you l squared t minus 2. Put it together, and the LHS is ml squared t minus 2. Now for the right-hand side, the RHS. Mass is m, gravity, g, is lt minus 2, and height h is l. Combine them, and look at that. You also get ml squared t minus 2. The LHS equals the RHS, so yes, the equation is dimensionally consistent.
Awesome. Now for its second use. Can we actually use dimensional analysis to derive a formula from scratch? Like for the time period of a simple pendulum? Let's give it a shot.
So what we do is we start by assuming that the time period t depends on the pendulum's length L, the bob's mass m, and gravity g, each raised to some unknown power, x, y, and z. Then, by writing out the dimensions on both sides of the equation and making them equal, we can actually solve for those powers.
And once you plug in those values you found for the powers, you get the formula T equals some constant k times the square root of L over g. But, and listen up, this is a very important limitation you need to remember. Dimensional analysis cannot, I repeat, cannot tell you the value of that constant k. Why? Because k is just a number without any dimensions. We only know from experiments that k is actually 2 pi. So, this method is powerful, for sure, but it has its limits.
Okay, team, it is time for the final lap. Let's do a quick rapid-fire round to see if these concepts have really stuck in your brain. You ready? Let's do this.
First question, nice and easy. All non-zero digits are considered?
Significant. You got it. That's the first and simplest rule of significant figures. If it's not a zero, it's always significant.
Next one up. What are the SI units for plane angle and for solid angle?
That's right, it's the radian for plane angle and the steradian for solid angle. And here's the tricky part that sometimes catches people out. Even though they have units, they are actually considered dimensionless quantities. Remember that.
Question number 3. Can you add velocity to force? Yes or no?
That's a big, fat no. And this is because of something called the principle of homogeneity. It's just a fancy term that means you can only add or subtract things that are of the same kind. You can't add apples and oranges, and you definitely can't add meters per second to newtons. It just doesn't make sense.
And for our very last question, a real thinker. If an equation is dimensionally correct, does that automatically guarantee that it's also physically correct? Think about that one. It's a small but very important difference. And that brings us to the end of our rapid revision. Keep practicing, keep working hard, and all the very best for your exam.